Okay, so in this lecture, what we're going to do, I was originally going to do the least squares for the quaternions, but I think what we should start with first is the quadratic equation. So although I gave a presentation in Boston on least squares, I think it's better that we start with a lecture on the quadratic equation over the quaternions. So the quadratic equation that you learned in high school doesn't work for the quaternions because they are a non-commutative algebra, okay? But when we get to the end of this, okay, we'll see that all quadratic equations, all the quaternions, ultimately have two roots, okay? And we actually solve it using a cubic over the real numbers, okay? So let's get to the beginning of the problem, okay? And I'm going to probably make a few revisions to this article as well before I resubmit while we're going along. And we're given the initial equation, okay? F, this is a vector that we know, equals x squared, which is the unknown, plus xb plus ax. Okay? And the first thing we want to do is turn this into c equals x squared plus xb. I'm going to stop writing vector symbols for a while. Just know that they're all vectors. Plus ax plus the product of two known variables. Remember, it's not commutative, ab. So then we're writing that c equals x plus a. This is the left-hand product, x plus b. And since we know a and b, that means we are setting c equal to the original variable f plus the product of ab. This is the first thing that we have to do, okay? So, yeah, I'm definitely going to revise this again, but for now, let's just go with what we have. So, the first thing we want to do is find the two-dimensional orthogonal basis in which our variables a and b existed. So, just to show you real quick, so you know this is not a waste of your time, here are randomly generated inputs for a, b, and f, and here are the roots, okay? And this closed form solution goes through the whole process, then uses the cubic equation calculator over the reals, and gives me my roots, okay? So, verify to work even with totally random inputs, okay? All right, so, confirmed by Excel. All right, so the first thing we want to do is we want to establish two variables. U is going to be the midpoint of vectors A and B. And V is equal to, we're going to change these to a more standard looking U because we're going to be using mu and U later. I don't want to confuse them. So U, okay, I'll do that. And V is going to be the difference between vectors B and A. The reason we do this is because the vectors U and V, they provide an affine basis, two-dimensional basis, in which vectors A and B exist. So this defines the two-dimensional plane upon which both A and B occupy. So this is the bisector of the two input variables, and this is the difference between them. Using this, now we go ahead and write C equals here we use A minus B. So we're going to use A minus B. So I'm like, wait, I think we should use A minus B because that will reverse the whole thing. So we're going to make this A minus B. Okay. You can derive it as B minus A as well, but I'm more familiar with A minus B being the way to do this. So now we have C equals, okay, the midpoint of the vectors, U, okay, and then you'll see here the identity for A is U plus V. So we get U plus V. And here we're going to get X plus B. B is U minus V. So now we get C equals X squared. And we're going to leave this in U plus V form. X times U minus V plus U. Remember, this is not commutative. Plus V. So X goes on the right here because this is on the left side into a right-handed X. Plus U plus V times U minus V. We get C equals X squared. We're going to still leave it in this form of U minus V for now. Plus U plus Vx. But this one will pound out. You get U squared minus UV plus VU minus V squared. This minus V squared is going to be critical in a moment. We're now going to make a substitution on X. We're going to say let T be equal to X plus U. So we're going to shift the original argument to U. So then we're saying that we're going to translate the argument. Okay, this happens a lot in the cubic and quadratic equations as well. You rewrite the variable over some axis of symmetry. And this is our axis of symmetry, U. Therefore, X equals T minus U. So what happens when we plug in here? Okay, we get C. So the original notation, I used the variable negative C. I'm actually more comfortable using just C. Anyway, so we have C equals T minus U squared plus T minus U, U minus V plus U plus V times T minus U plus, we're going to bring that down, U squared minus UV plus VU minus V squared. I just want to check, make sure the video is actually recording. UV plus, okay, fantastic. Okay. All right. So let's go ahead and, well, FOIL it all out. So C equals T squared, okay, minus TU minus UT plus U squared. Then we get here plus TU. So this already canceled. Okay. Minus TV, which won't go away. Then we have, so what I'm going to do is leave the terms I don't know cancel out. I'm going to put them in purple. Okay. Minus TV. Then we're going to get minus U squared. Okay. and then plus uv. That's going to cancel with up here. I'm not going to bring it down because it's going to cancel. So this cancels. Then we get, okay, the next statement here. We're going to get plus ut. Well, that just canceled with here. And then we get minus u squared, which cancels with this u squared from this term that we brought down. And then we get plus vt. This will stay. And then we get plus vu. Sorry, minus vu, which will cancel with this term. And then we get minus v squared. So we get c equals t squared minus tv plus vt minus v squared. Now, if t and v were real or complex numbers, this would be 0. So you just have c equals t squared minus v squared. T squared equals square root v squared. That's usually why I use negative c, but we'll just say plus c or whatever, minus c, however you want to do it. The thing is, for the quaternions, anything in the form of xy, well, I'll use different letters, vectors mn minus nm does not cancel out to 0. In fact, the result, we'll call this p, the resulting vector is always orthogonal to both m and n. So this expression is some vector that is orthogonal to both t and v, and only v is known and c is known. So what we're going to do here is we're now going to write d equals t squared minus tv plus vt. And we're going to deal with this in a moment. And that's it. Where d equals c plus v squared. So d is known, v is known, t is the thing we're trying to solve for by substitution through x. So what would be the next step here? Okay. We're going to have to go into a bit of theory, but let's go ahead and write what these are at the moment. So we know this would be d null, and q is the real vector, the forward vector, okay, plus d1i plus d2j plus d3k. T is completely unknown, but v is not. V, this is the vector d. V is equal to v null. Q, that's the real part. This is my real vector. I actually notate it as a vector. v1i plus v2j plus v3k. Now, before we can proceed any further from here, we're going to need a couple of general theorems that have nothing to do with the quadratic equation before we can proceed any further. However, before we do that, let's go ahead and examine other forms that we could have reduced this to. Okay? So we call this the fundamental middle-handed form. because this is equal to the v part, we could have wrote d equals t squared, okay, plus negative v for, from the left, this would be the matrix equivalent, the matrix identity of a left-handed quaternion, plus the direct entry sum of v for right, you add these two matrices together, times t. There is, however, a right-handed and left-handed form where we can write d equals w squared minus 2wv, or d equals w squared plus 2vw from the right. And the substitution is just to set w equal to t, in this case minus v, and here the substitution is w equals t plus v. However, this apparent simplification is actually impossible to solve in that form. So rather, the form that we need to solve it in is this one. And the reason this is solvable is because we know that this result of this operation is a vector that's both orthogonal to t and v, allowing us to do some basic trigonometry to put together a cubic equation to solve for t. Okay. All right. So what is this? What is it that we have to do from here before we can proceed? Okay. So we're going to take a step back and we're going to go through what's orthogonal imaginary bases. So here we have, I'm going to bring this into Paint, okay? We know that ij equals negative k, ik equals positive j, j equals negative I. But I, j, and k is only one set of pairwise orthogonal imaginary vectors in a continuous, well-defined three-dimensional subspace. So when we're given a vector in the form of, we're going to look at an imaginary vector with no real part. Let's say we have w equals w1i plus w2j plus w3k. We can write this as simply w equals, we're going to set capital W to the magnitude of this vector, which is just the square root of w1 squared, w2 squared, w3 squared. Write this as capital W times lambda, where lambda is a purely imaginary unit vector. Okay, so how do we find that? How do we do that? So here, I give the process here, and it's nothing that's actually truly new. But we need to do this, we have to convert ijk to the proper basis that allows us to solve this problem, because it's unsolvable in ijk format. So what we do is we take the four-quadrant arctangent of w1, w2. So we say let alpha be equal to a tan 2 w2 over w1. This gives us the angle in the ij circle. So if we draw the ij plane, okay, this is I, this is j, and this is our coordinate w1, I, w2, j. What we're looking for is this angle here. This is theta. Then what we do is we take another arctangent function. We'll say beta. Beta is equal to, again, a tan 2 W3, which is the k component of W, over the positive square root only of W1 plus W2 squared. So this let's call this vector W1, W3 the unit vector. Let's just call that, just give me a letter right now. Call that the z vector. Okay. So now we're looking at the angle. If we were to draw another unit circle with the W vector as the x-axis, and the k vector as the y-axis, okay? We now want to get the coordinate, and let's say that W1 plus W2 squared, let's give that a value. Let's call that, z. Okay, so this is the z unit vector, and let's let capital Z, okay, be the magnitude, which is that square root of W1. W2 squared. Okay, so we're writing this as capital Z magnitude, real number times Z. And again, wherever that coordinate falls, let's say it was down here. This was Z times the unit Z vector plus W3K. Then we're looking for whatever this angle is here. So this is the beta angle, and up here we have the alpha angle and the IJ circle. We now go ahead and rewrite lambda, okay, which is the unit vector that we're seeking to write as ijk, is going to be equal to, and I have it right here, is equal to positive I cosine alpha cosine beta plus j sine alpha cosine beta. Because remember, the reason we have cosine beta appearing twice is because beta is the z vector, and that is the angle to the W3K coordinate, okay? And then we get plus k sine beta, which is the sine of this angle. This is the k coordinate. So now we go ahead and write, well, W is also equal to the real number magnitude, W1 squared, W2 squared, we call that capital W, times lambda. And we define lambda as the rotation of I to lambda using this. However, there are now two other axes that are perpendicular to our lambda vector. So when I moves to lambda, J is going to move to mu, and K is going to move to nu. So to guarantee that they remain orthogonal and in the same orientation such that the rules of multiplication are the same for the quaternions I, J, K, we now say, and so let mu be a vector, a purely imaginary unit vector orthogonal to lambda, and that's equal to negative I sine alpha plus j cosine alpha plus 0k. We're only using alpha because we're taking the ij circle and we're rotating I by this angular argument to here. And that means j is going to rotate to a 90-degree angle here. So this is mu. We're rotating them by the same argument. But we don't have to interact with the third dimension of k for mu. And then nu, we do have to interact with the third dimension. So here, it's almost the same as lambda. Okay, so nu, but it's 90 degrees off, okay, is negative I cosine alpha sine beta, okay? So if you took a coordinate cosine theta plus I sine theta, you can rotate that 90 degrees by just writing negative sine theta plus I cosine theta. That's a 90-degree rotation. That's the same thing as multiplying by I, okay? And that's what's happening here. We're multiplying, instead of by cosine, we're multiplying by negative sine. And then you get plus j sine alpha, which is the same as up here, times positive sine beta. That stays. And then our last coordinate isn't sine, but now cosine, plus k cosine beta. So what this does is it just takes the three axes I, j, k and performs a rigid body rotation to a new set of axes that are pairwise orthogonal, lambda, mu, and nu. And they retain all the exact same properties as the regular quaternions when they're multiplied. So they're not regular, they're just quaternions, but with a different orthogonal axis, okay? A different orthogonal basis. So you can take this quaternion multiplication table, and as long as you perform the rigid body rotation exactly as prescribed, then you're going to get, instead of q I j k, q I j k, giving you q is the same thing as 1, okay? Q, negative q, negative q, negative q, I, negative I, negative j, 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 k, negative k, k, k. We just replace this with lambda mu nu, and it's the exact same table, as long as you perform the rigid body rotation that way, okay? So now we just have q lambda mu nu, q lambda mu nu, and you're going to get the exact same table. You're just replacing the symbols, okay? It's elementary school. Q, negative q, negative q, negative q, lambda, lambda, negative lambda, lambda, mu, negative mu, mu, mu. Finally, nu, negative nu, nu, nu. So that is what the rigid body rotation, okay, of ijk to lambda mu nu does. So it preserves the multiplicative relationship that we're already familiar with. All right, so why did we have to talk about this before we proceeded with the quadratic equation? Okay, because we cannot solve the quadratic equation over the quaternions directly in ijk form. Instead, what we're going to do is write v as equal to the real part v null q plus n lambda. We're going to attune the entire quadratic equation to the imaginary unit vector of v, okay? Where n equals the square root of v1, which is the I component squared, plus v2 plus v3 squared. Then we're going to write our angles. Alpha equals a tan 2. The j portion, v2, over V1. Beta equals A tan 2. V3, which is the k coordinate, over the magnitude positive square roots of the I and j coordinates. And then we're going to use that identity. Lambda in respect to v is equal to, I actually forgot, I gotta go look. I can't remember everything. Let's look at the damn paper. How's that for an idea? Okay. Over here. Okay. And then lambda of v, okay, is going to be given by positive I cosine alpha cosine beta plus j sine alpha cosine beta plus k sine beta. We now have to define mu1 and mu2. So here's the thing. Okay. Let's just say we have our axes, lambda mu nu, in this three-dimensional subspace, okay? And what we're doing is taking ijk and we're turning that into lambda. And this is going to be mu. And this is going to be nu. So this green circle is the mu nu circle. Okay. However, you define these axes in mu nu space. There is no preferred reference frame in respect to lambda to which we have to hold mu and nu to. You can actually rotate mu and nu again within this two-dimensional subspace. And so long as you preserve the orthogonality between them, they will still uphold the same multiplicative properties. So you can take, in other words, you can replace mu and nu in this table with mu2 equal to mu1 cosine any angle gamma plus nu1 sine gamma, and nu2 equal to negative u1 sine gamma plus nu1 cosine gamma. And as long as you rotate mu nu, or the original axes, according to this, the nu property will still hold for mu2 and nu2. Sorry, the normal properties will still hold. So what this does is it gives us flexibility in solving the quadratic equation, that we are going to reorient not the lambda axis. The lambda axis is fixed. It's defined by v. But we can and will reorient the mu nu axes in such a manner that makes the problem easiest to solve. Okay? First, though, we have to find mu1 and mu1 based on the generic definitions. Okay? So we're going to get mu1 is equal to negative I sine alpha plus j cosine alpha plus 0k. And then we get nu1 equal to negative I cosine alpha sine beta plus j sine alpha sine beta plus k cosine beta. So where does mu2 and mu2 come in? Well, that actually comes with d. Okay. So the first thing we have to do is take d in this form, and we now need to write it as an equivalent vector, but not with I, j, k axes, but with the lambda mu nu axes. Okay, that's what we have to do here. So we need to do an orthogonal basis conversion. How do you get from here to here? Okay, so we already know what the vectors are. So what we do is we create a matrix, 3 by 3 matrix here. You don't have to do it this way, but this is the easiest way to do it. And we're going to write this more simply as lambda equals gamma 1, 1 I plus gamma 1, 2 j plus gamma 1, 3 k. Mu will be equal to gamma 2, 1 I plus gamma 2, 2 plus gamma 2, 3 k. And nu will be equal to gamma 3, 1 I plus gamma 3, 2 j plus gamma 3, 3 k. And this will be a matrix. We're going to call this matrix now M. And what we're going to do is then write D as a column vector next to it. Okay. D. We're going to put our D1I, D2, D3J. And what we're looking to solve is for the conversion. We're just going to call this. I need new letters. So we'll call this Y1, okay, Y2, Y3. We're going to take the inverse of this matrix and then multiply it by this column vector, which will solve for Y1, Y2, Y3, all real numbers. And out will pop our coefficients, D. Remember, we're not changing the real part, but we're going to get D. We'll say this was D1 null, T3 null. D1, 1, which is actually what we're solving for. So this is like D1, 1, okay? Lambda plus D1, 2. I should say D2, 1, mu, 1. D3, 1, nu, 1. Okay? That is the conversion from Qijk to Q lambda mu nu. It's the same exact vector, but now being expressed with a different orthogonal basis. Okay, now that we have that, we're now going to say these two new coordinates that pop out here We're going to say let omega be equal to the square root of d2, 1 squared plus d3, 1 squared. That's the magnitude of this mu portion of the d vector. And now we're going to say let psi be equal to, I'm going to shrink this a bit. So we're going to say let omega be equal to the real number magnitude of the mu portion of d, and let psi be the angle a tan 2 of these two coordinates in mu space, d3, d2, Then we're going to define mu2 as mu1 cosine psi plus nu1 sine psi. And we're going to then define nu2 as negative nu1 sine psi plus nu1 cosine psi, which then says that d is equal to d null q plus d1, 1 lambda plus omega mu2 plus 0. This is a huge step. mu2. And v, okay, v we're going to go to the next slide here. V is equal to v null q plus n lambda plus 0 mu2 plus 0 mu2. Okay? So now we have an equation that says the d vector is equal to t squared minus tv plus vt. And we're going to define the unknown t in the same way. T, even though it's unknown, is equal to t null q plus t1 lambda plus t2 mu2 plus t3 mu2. We're going to address this very shortly, but let's look at what the square of any quaternion is. T squared is therefore equal to, the real part is t null squared minus t1 squared minus t2 squared minus t3 squared. That's the real part q, plus 2 t null t1 lambda plus 2 t null t2 mu2 plus 2 t null t3 mu2. Okay? That is the square of any quaternion for ijk or lambda mu nu. Doesn't matter. Okay? Now we got to look at negative tv plus vt. So let's say we have the vector. Now I'm going to prove that there's no real or lambda part to this. Negative tv plus vt, okay, is equal to t null q plus T1 I plus T2 J plus T3. Oh, I should have lambda mu nu here. It's all isomorphic to me. You could literally write IJK, I wouldn't care. Mu2 and U2 times V, which is V null Q, plus N lambda. Okay? And has no mu and u parts. I'm going to leave that out. I'm not going to write 0, 0. Remember, this is the negative. Okay? Plus the same thing. It's going to copy and paste it. But the other one, V, is now coming from the left side. We're going to get plus this expression. So let's isolate the first two parts. So T null Q T1 lambda, this part times this, okay? The negative of that times this segment is actually commutative, so it cancels out. So Q times Q, which is the real number dimension, the forward vector, is the identity. Okay? So we're just going to write it out. You get, just to show you that it all cancels, T null, V null, Q negative, minus T null, N, well, Q times lambda is lambda, it's the identity vector. Okay, lambda. Then here, we're going to get V null T null. V null, well, real numbers are commutative, so that's thing, times Q. And then here we're going to get plus N T null. Lambda times lambda is, I didn't even FOIL out the whole thing. Okay, so my bad. We'll go ahead and do this. Okay, so then T1 lambda times V null Q is equal to plus T1 V null Q, and then lambda times lambda is -1. So we're going to get minus T1 N, which is a real number, so we put Q. Now here, we get the reverse. So we get V null positive, T null, real numbers commute, okay? Q, and then V into T1, we're going to get plus, we'll do it over here, plus V null T1, Q times lambda is lambda, and I meant to write a lambda here as well. Lambda, okay, and then we get N T null, so we get plus N T null. Lambda times Q is positive lambda. And then we get plus NT N T1. And then lambda times lambda is -1. Okay. So we should get minus, we get minus here. And then the other one was actually plus, because up here we have lambda times lambda, which is -1, but a minus sign, which is positive. Okay. So what ends up happening is that the real and lambda portions all cancel out. So there is no real, or lambda portion left. And you can go through the math yourself. I'm just going to shortcut a little bit here. The end result of this expression, after everything cancels out, okay, is going to be 2n t3 times mu 2, because it's going to take the t3 mu coordinate of t and put it into nu, because it's a rotation of 90 degrees, minus 2n t2 mu 2. This is going to be the end result. And this vector is orthogonal to lambda. It has no lambda parts. Okay? And it's also orthogonal to our unknown t variable, and therefore our unknown t squared variable. So what we end up with is a system here. In mu nu space, if we draw what's actually happening, we have some vector t2, t3 that then gets scaled by 2t null. Let's say this was t2, t3, and it gets scaled out to here. And then you get some vector that's orthogonal. Okay, and this is the vector negative tv plus vt, and this is the mu nu portion of t squared, and this is the t2 t3 coordinate in mu nu space. And because we know that there's a right angle between these vectors, then what we're essentially talking about is a right triangle in mu nu space. So that's what the whole problem boils down to. Okay. So again, here's a better picture of what's going on here. Okay. So if we go back to where we left off there, we now have an equation that says d, okay, which is d null q plus d1 lambda plus d2 plus omega, which is a very important variable here, d mu 2 plus 0 mu 2 is equal to t squared minus tv plus vt, which is equal to the real lambda parts don't even apply, t squared plus 2n t3 nu 2 plus t2 nu 2, which gives us a system of equations for each component of d. So then d null is equal to, that's the real part, it's equal to t null squared minus t1 squared minus t2 squared minus t3 squared. That's the real part. d1, we're just going to write it as 2d null, 2t null t1. There's no simplification beyond that. But then d2, which is omega, is now equal to 2 t null t2 plus 2n, okay, 2n t3. And then 0, which is the new portion of our d vector, is equal to 2 t null t3 minus 2n t2. And we'll just skip to that now. So here we're at here in this paper, if you followed so far. So when you take this system of equations, you end up, well, T null equals n T2 over T3. And then you solve for T null again, and you get T null also equals omega minus 2n T3 over 2n T2. We now set these two equal to each other, and we get 2n T2 squared when you cross multiply equals omega T3 2 or whatever. So then we just write, and therefore T2 squared equals this expression. So we now come to our d variable, okay? And now we know what T2 squared is in terms of T3. Okay, that's T2 squared. All right, now what we do is we go and solve for the same exact equations again for T2. So we get an equation involving T null and T3. We solve the other one, and we get T null equals something with T3 and T null again. We set these equal, and then we get T null squared is equal to this expression. Okay? And since we know that that means 1 over T null squared is equal to this expression. And we know that d1 lambda is equal to 2 T null T1, which means that T1 is equal to d1 over 2 T null. So when you square it, you get T1 squared is equal to d1 squared over 4 T null squared. Well, isn't it nice that we have the reciprocal of T null squared here? So when you multiply that all together, we end up with T null squared equals this expression here. So what we end up with is an equation in one variable that can all be taken back to the coordinate T3 mu 2. So d null equals this minus this minus this minus T3 squared. Now I'm going to save you the horror of this part. You can go through it all you want on your own in the actual document link. But when we combine all of these parts, and we have to get common denominators and numerators, what we end up with is a cubic equation that says the following. Okay? Zero equals something t cubed, something t3 squared, something t3, whatever. That's just a cubic in the form of a t3, b t3, c t3d. And here is the variables, and omega is known and n is known. D null and d1 are known, so all the variables are known for a, b, c, d. So you go and solve for the real root of this cubic, okay? We use Cardano's theorem, then we use Vietta's substitution. This is stuff from the 16th and 17th centuries. It's well documented, well known. And then we have a problem, okay? So we get our roots to the cubic using Vietta's substitution for T3. But now you're left with these weird identities. T null equals this, T1 equals this, T2 equals this. Which sign, which root? How do you know which roots to choose? Well, we already have T3. Let's go back to the geometry of the situation, okay? And we're going to go pull this up here. So the system of equations here for T1 and T null initially, this expression here actually forces the T2, T3 coordinate to be on a circle that is offset from the origin by omega over 4n. Okay? So here is the vector t squared, this blue line from here to here in mu nu space. Here's that orthogonal vector, negative tv plus vt. But here is the t2, t3 coordinate, and it must exist on a circle of radius omega over 4n, offset from the center by positive omega over 4n. So now, if we were to say what is the magnitude of this vector, then we were to go write our coordinate that is still technical. Well, we know the t3 coordinate now from the cubic, but we're going to say let t2 mu2 plus t3 nu2, just let that be equal to some real number magnitude cosine z mu2 cosine z plus nu2 sine z. Okay. Then what's happening is we can actually determine the magnitude, okay, of that vector, even though it's technically still unknown, but we can define it as it's unknown as of the moment. We can use the law of cosines to get that magnitude. So since it's offset, the circle is offset from the origin, we know the radius. It's right there. It's a vertical offset. And then we have an isosceles triangle. So if this is theta, okay, then this is pi over 2 minus theta. This is pi over 2 minus theta because it's an isosceles equilateral. And then this must therefore be 2. So when you use the law of cosines, the magnitude of this mu2 coordinate, t2, t3, is equal to 1 over, it's omega over 2n sine theta, okay? And we can see that here. Maybe it was 4n, let me be sure. Anyway, here's a derivation using the law of cosines, omega over 2n sine theta. So if we remember that from this system of equations here, 0 equals this, well then let's divide by 2 equals t null t3 minus n t2, okay? Then we're saying that t null is equal to nt2 over t3, which is equal to n times m cosine theta over n sine theta, which is equal to n cotan theta. So we can define t null as simply n cotan theta. And you see that here. And then t1 equals d1 over t2 t null, so we write that as d1 over 2n tan theta. Because if you divide d1 by 2n cotan theta, that's what you get. Cotan, the reciprocal is tan. So now we have a polar function for all of our coordinates. So now we have t t2 equals 1 over 2n sine theta cosine theta, and t3 equals 1 over 2n sine theta, which is sine squared theta. Okay, great. So what that means then, if t3 equals 1 over 2n sine squared theta, and we know what t3 is because it's the roots of a quadratic, then we get theta equals arc sine of the square root, because we're going to take the square root of that sine, okay? 2n t3 is omega. It should all be over omega. Over omega, okay? Or maybe it is, I don't know, let me take a look. Is omega in here? Yeah, okay, so there is an omega in there. So forgive me, it was omega over 2n sine theta. But anyway, so this is what you get. So you need the arcsine of the root. Now, you might say, well, which arcsine do you take? Well, you actually take both. So you take theta and pi minus theta. We call this theta 1. And theta 2 equals pi minus theta 1. We take both arcsine arguments, not because we can't resolve the ambiguity, but because both results of the arcsine formula will fulfill the quadratic equation. So what we do is we get this cubic, we get T3, we find the real root of this cubic, there's only one, we pop it through, then we take the arcsine of 2n over this cube root T3, whatever, you take the positive square root because we know that T3 is a positive number in this positive circle. That's in the quadrants 1 and 2. So we even know to take the positive square root. And then we fill in T null, T1, T2 according to cotan, tan, sine, and cosine. And out pops all our roots. Okay? And that's pretty much what you do. And then once you have them, of course, you have to go and convert back to IJK. So we're going to close this lecture with the general process now. So you start with f equals x squared xb plus ax. Then c equals f plus ab. Negative c equals x squared plus xbax. U is the midpoint of AB, V is the difference of AB, giving us that two-dimensional basis that describes, that captures A and B. Then we have the substitution on X, T equals X plus U, X equals T minus U. We go ahead and we do whatever we do. Then we subtract, we add V squared, which is the difference from A to B, to C, and we get D. Okay, and then D is written in this form, and this variable is known. V is known, but T is not. So we end up with D equals T squared minus some vector that's orthogonal to both V and T. And then V equals this. We then find lambda in respect to V. That is the imaginary unit vector that describes V. Using the arctangent arguments for alpha and beta, we also get the other two orthogonal axes to lambda, the generic ones, mu1, mu1. And then we then convert D into that form, okay? We convert it from IJK form to lambda mu1, mu1. We find the real number magnitude of the mu1, mu1 coordinate of D. We call that omega. And then we get the angle of that coordinate, and then we rotate mu and nu, the generic axes, into the specialized axes, mu2, nu2, allowing us to now write D as simply D1 lambda plus omega mu2 plus 0 nu2. We then run our cubic equation using these coefficients for A, B, C, D to yield T3. This is Cardano, and then this is the Vieta substitution. And then whatever the roots are, technically, I'm not going to get into this in this video. Just take the real root. Technically, all roots work and give you the exact same result, but that's beyond the topic of this video. And then theta equals arcsine of the positive square root of 2n times the real cubic root over omega. I explained in this paper what to do with the other roots, but we're not going to go into that here because it's just most practical to take the real argument. Okay, and then you get your coordinates T1, T2, T3, whatever. You get both roots. We now got to convert back to IJK. So now we do an orthogonal basis conversion back to IJK, and we get T1 and T2 in their IJK form, which is generic. And then remember, x is equal to t plus u. So now we take u and subtract that from t, and out pops our roots x1 and x2. QED, the end. So if anybody has any questions about this, you can leave them in the comments, or I'll even show you in private. Just email me. Okay, Edward, I'll write it here. EdwardKingSolomon@gmail.com. I'll be happy to walk you through this in private if you need. Just wanted to show you the general method, and here is a calculator. I'll put it in the description. And what you do is you put the original vector inputs f equals x squared xb ax. You put f here, put b here, put a here, and it will go ahead and do all of the steps that I described. And here's a cubic equation calculator that you can use in your own time that just does cubic equations in general. You put the a, b, c, d, and then the imaginary a, b, c, d coefficients, and out pops your 3 roots here. Anyway, your roots for x1, x2 will pop out right here. Sometimes the way that if you have a very extreme cubic, you might get some floating point error. So I put the decimal tolerance so you know that these roots are fulfilling the equation for each vector component within that decimal tolerance. You can set that to whatever you want. And it checks that over here to make sure that you're getting the same thing back, okay? And that's it. So I'm going to put this in the link to the video as well. And I hope you enjoyed it, okay? See you all later.